Okay, I'm just going to test my transcription. Okay, it seems to be working. I'm sharing my screen. So good morning, everyone. Hope everyone had a good week off. Now we're back to school and everything and back to our lab 3. So of course, just everyone would know that we have our midterm on a couple days here on Thursday. You have all day Thursday to complete the midterm. I'll be on and off of email. We're going to email to answer any questions that may come up. So again, check out the practice exam. I see about 4 of you have so far, so hopefully more of you will have a look at that before Thursday comes around. So today's lab has to do with what we've been looking at in terms of basic probability, and also looking at things like Poisson probability and binomial probability distributions. So it's basically going to be using Excel and JASP. The first part of the lab has to do with some basic probability, like for question 1 and question 2. Question 1 is pretty straightforward. It just lists a few regions here, right? 23 countries in North America, 12 countries in South America, 47 countries in Europe, so on and so forth. And basically what we're going to be doing here is filling in the probabilities to 2 decimal places of, right, probability of S, right, would be the probability that a country, that the event happens in a country that is in South America. So the idea here is that the event has an equal and random chance of occurring in any of these regions, in any of these countries. So based just on the relative numbers assigned to each of these countries, you're going to figure out the probability of each of these events. Second question, basically similar to the first question, but it's using what's known as a Venn diagram to visually represent our probabilities. So in this, we looked at this example in lecture, where we're looking at the what's known as the mutual overlapping exclusive probabilities between 2 events, somebody liking ice cream versus somebody liking soccer. And then where we have an overlap, right? We have a non-mutually exclusive events in 5 and 6. And the way that this question is set up is that we have 4 people that only like ice cream. We have 3 people that like soccer. We have people 5 and 6 that both like ice cream and soccer. And then we have 4 people, 10, 11, 12, 13, that completely do not like ice cream or do not like soccer. So based on that, having 13 people in total, you're going to be calculating based on this Venn diagram, right? Things like the probability of finding somebody who likes ice cream. So I'll give this one away, right? So the probability of somebody liking ice cream, we have 13 people total, and we have 4 people that just like ice cream. Our probability is divided by 13. So that's how you're going to be determining those basic probabilities for question 1 and 2. Question 3 has to do with the binomial distribution in an Excel spreadsheet. So what you're going to do is you're going to download this Excel spreadsheet right here. Let's go into my download box. And when you open it, you see that it's going to have 2 tabs. First tab is called Binomial Birds. One is called Poisson Hailstorm. So the first one we're going to be dealing with is the binomial bird. Remember, a binomial probability distribution is one where there's only 2 outcomes, right? On or off, yes or no. So in this case, the question is binomial because it's whether these ornithologists see a certain bird or not. And it's given that the chances of success of them seeing this rare bird species is 50%, 0.115. And how many times are they going to go out? Then this year is 32 times. So what you're going to be doing in this spreadsheet is using the Excel expression binomial to determine the probability of these ornithologists going out and seeing no rare bird species, 1, 3, 10, 15, or 20 rare bird species over these 32 times they go out. So how we do this in Excel to calculate the binomial distribution, and I showed you this in lab, is that you can use the expression. So I start to type in binomial, and you can see there's my binomial distribution. I'm going to click on that, and it's going to ask me to input a few things. First thing it's going to ask me is to input the number, or number of successes. In this case, it's going to be 0. If I enter that, point to that cell right there, comma. Now it's asking me the total number of trials. So total number of trials in this case is 32. Another comma. Probability of success on each trial is 0.15. So I'm going to click on that cell there. Another comma. And then it asks me whether it's cumulative distribution or not. In this case, I want to calculate the probability for each of these discrete events. So in this case, I'm going to select false. I do not want it to be cumulative. I close bracket and I hit enter. So you can see there it's determined the probability here of these ornithologists to go out 32 times. What's going to be the probability that over those 32 times they go out, they're not going to see any rare bird species. There it is according to the binomial distribution, and there it is just rounded to the 1 decimal place. All right, so that's what you can do for the rest of these cells. Now, kind of a trick here, so you don't have to retype in the expression every time, is that you can go and grab that bottom right corner of the cell and drag it down. You can see if you do that, there's a problem. And if you click on the cell, you can see what the problem is. Because when you drag down, it dragged down to 1, which you want, but it also dragged down on these cells up here. So the way to avoid that is that if you go back up to your original expression there, so I'm going to delete that from the second row. I'm going to go up here and I'm going to lock those two cells, so the 32, total number of trials, using a dollar sign. So I actually want to use the dollar sign. I put it in front of the 8 because I do not want it to drag down when I drag the box down. And I'm going to put it in front of the 7. I'm going to keep everything else the same. So now when I drag down and I click on the cell, you can see that it's now looking at 1. That's a discrete probability, but it's also now staying on those two cells that I want. So if I just drag down, it should complete, right? Complete the probabilities for each of these number of bird sightings like that. So another thing that it asks is that what is the probability that the ornithologist Bob and Sarah will see less than 7 rare bird species over the 32 trips? So I can do the same thing. I'm going to type in binomial. I'm going to click on 7. That's the number of successes. I'm going to go up and I'm going to click 32 trials again. I'm going to click on 0.15 for the probability of success on each trial. But this time I'm going to click true. And what that does is that it gives me the cumulative, all the probabilities up to the number of 7 rare bird species. So in this case, right, there's a 90.4% chance that if they go out 32 times, they're going to see, right, 7 or less rare bird species in those 32 trips. That's how you're going to go about doing the binomial distribution. Of course, there always is an embedded video there to take a look at that. And you're essentially going to be filling in these values from the Excel table that we just did. Same kind of idea, but now we're going to be looking at the Poisson distribution. I'm going to go back to my Excel table. It's on the second tab there, Poisson hailstorms. So this example gives us, and again, we've done similar example in the lecture. It gives us this table where it lists the number of hailstorms and how many years each of these numbers of hailstorms has occurred. We've also determined the total number of hailstorms just by multiplying column A and column B. And we've summed up both column A and column B and column C. So we've got to do a few things here. First thing we've got to do is determine the observed probability of occurrence. So to do this, what we have to do is divide each of these observed frequencies. How many times 0 hailstorms were observed was 10 years. So 10 years divided by the total number of 35. So there's the observed probability of occurrence, right? 0.286 for 0 hailstorms. Same kind of problem occurs though if I drag down, because now, right, the expression is looking at 13 in the next row down, but it also has dragged down. I want this cell to keep looking at 35 in total. I'm going to do the same thing here again. I'm going to delete this. I'm going to lock cell B14. So now when I drag down, it'll keep looking at the cell, right? And I know things work because all of my probabilities in that column have added up to 1. Now for the Poisson distribution, I need a couple things. I need also my mean probability of a hailstorm occurring on a year. Now to do that, all I have to do is simply take the total number of hailstorms, which is 42, divided by the observed frequency of years. So that gives me a mean probability of 1.2 hailstorms per year. So now I have everything I need to calculate my Poisson distribution, which is basically giving the probability of seeing or observing 0, 1, 2, 3, 4, or 5 hailstorms. So in Excel, the way that we do the Poisson distribution, you can just type in =PO, and that's the expression right there. So in this case, I'm going to be looking at, right, number of hailstorms, which is the X. I'm going to also look at the mean, and I also want to lock it on the mean because I do not want the cell to drag down. And then I'm going to click false because I want this to be discrete probability. So you can see there, it's looking at 0 hailstorms or an average of 2.2 hailstorms per year. So when I drag down now, right, I can see it almost adds up to 1. It doesn't add up to 1 because there's a bit of some rounding errors there. That's how you determine your Poisson distribution probability. So you can see that in this case, we have the greatest probability of observing 1 hailstorm, right, which has a probability of 0.361. So it also asks you to make a bar graph showing the probability of observing X number of hailstorms per year, right? So to do that, I can drag over top of my probabilities. I can go to and then basically I can add my titles and whatnot, and there's my probabilities right there. Again, greatest probability for seeing 1 hailstorm. So one thing I do have to do here is I have to go to select data, and I want this to look at the number of hailstorms. So I'm going to drag over top of that column there. And now when I go down, I can see that, okay, that makes sense. I have the greatest probability of observing 1 hailstorm, and then after 1 hailstorm, the probabilities decline after that. So you're going to be making a column chart like that. Then you're also going to be making a scatter plot between the predicted Poisson probabilities and the observed probabilities to see how good of a fit there is. Because the closer the fit between the Poisson probabilities and the observed probabilities, the more likely that our data set is random in nature. Again, if you wanted to make a scatter plot, you can drag over top of a column, go to scatter, right click on the plot itself, go into select data, and then I can click on, oops, let me move this chart out of the way, right click again, go into select data. Now I'm going to tell it to look at the observed probability of occurrence for the x-axis. So there's my scatter plot between the observed and predicted or Poisson distribution. And remember, of course, to put in your axis titles, right? Observed probability versus Poisson probability. Save it as a picture file along with your column chart and upload those. Then upload those files in the Dropbox down here in image format. So question 6, right? Does the hailstorm data follow a normal Poisson distribution? Basically, you're going to be looking at your scatter plot to determine whether yes or no. Okay, the second part of the lab, we're going to be using JASP. So the data input file that we're going to be using is this one right here. Again, we're looking at snow depth data from Mason Lake. And essentially what we're going to be doing is that we're going to be opening JASP. And so let's open JASP here. Take a couple minutes. I haven't opened it for a couple days here. There we go. And I'm going to go new data. Oops, sorry. I'm going to go open. And I'm going to go to my computer. I'm going to go to my download box. Here's my Mason Lake snow data. It's going to take a couple seconds to import it from the CSV file. So the first thing you're going to be doing while that's uploading is that we're going to do some basic descriptive stats. Okay. So again, we have two sites, J1 and J4, and we have different variables, snow water equivalent and snow depth. Snow water equivalent, right, SWE, how much water is in the snow. So the first thing we're going to be doing is calculating the mean and standard deviation in the table below. So to do that, I'm going to go to my descriptives tab there, descriptives, and I'm going to, for my variables, I want to look at SWE and depth, and I want to split them by site. Right, so there I have my standard deviation, my mean, right, for both J1 and J4 sites, both for the variables SWE and for the variables depth. So that's essentially what we're going to be doing. We're going to be entering those values in this table for question 7. A few more descriptive stats. We're going to be looking at the skewness and kurtosis, right? So I'm going to go back to JASP, under the stats there, under distribution. I'm going to click the skewness and kurtosis boxes. So you can see I get those values there for skewness and kurtosis. Right, so by looking at those values, right, you're going to determine where the skewness is for SWE, for J1 is symmetrical, highly negative, positive. What's the best descriptor for that? Just plunk it into the box itself. Similar kind of idea, right? Or depth. And then you can also, right, you can also visualize our data. So I can go down here and I can do some basic plots, right, some distribution plots to see how my data is distributed. So I click the distribution plots. It takes a couple seconds for it to upload. Right, so I basically have a histogram here, so I can tell just visually whether I have a skewed data set for each of those sites and variables, or whether it's skewed or whether it's platykurtic or leptokurtic. Remember, platykurtic is the really flat distribution. Leptokurtic is a very pointed distribution. Another way we can test for normalcy, if our data is normally distributed or not, is that we can create a QQ plot. Now, we also did look at this in class. So I'm going to go here under basic plots. I'm going to click the QQ plot. So QQ stands for quartile and quartile. It basically compares the theoretical distribution or normal distribution to your actual data set. So the idea here is that the closer the points, these dots are along this line, the more normally distributed your data set is. So you can see down here for J4, right, this last data set here, this for me would be the most normally distributed data set because the dots line up closer to the line compared to this data set up here where you can see that there's some deviation from that perfect fit line. So you're going to be doing a few QQ plots there, right? QQ plot for SWE at site J1, QQ plot for depth at site J4, right? And you're going to be saving those plots from JASP and entering them in the Dropbox below. Now the last thing kind of test that we can do for to see if our data set is normally distributed or not is do a Shapiro-Wilk test. So to do a Shapiro-Wilk test, we're going to go back into JASP here, and I'm going to go back up to my basic stats, and just under where my skewness and kurtosis are, I'm going to click the Shapiro-Wilk test. So that's going to add a couple of values to my descriptor table. You can see them here, Shapiro-Wilk, and p-value of Shapiro-Wilk. And so the idea with Shapiro-Wilk, as we discussed in lecture, is that the null hypothesis, basically our default hypothesis, is that our data set is normally distributed. It's only if we reject that null hypothesis is that we're going to say that we're not dealing with a normally distributed data set. Now, how do we tell if we're going to reject or not reject our null hypothesis? Well, basically, we're going to be looking at what's this p-value of the Shapiro-Wilk. So wherever we have a p-value, which is less than 0.05, that's going to be our threshold, our alpha value, we're going to reject our null hypothesis. So you can see here, we actually only have one site and one variable where we have a p-value that's less than 0.05. And therefore, we would reject the null hypothesis that our data set is normally distributed. So that's how you can interpret the Shapiro-Wilk test, right? You're going to click which of these variables and sites is normally distributed or not. Essentially, what you're going to be doing here for question 15, you're going to be entering the Shapiro-Wilk test stat and also its p-value. So go back up here. Here, the Shapiro-Wilk, that's the test stat right there, that 0.954 for site J1 for SWE. And then you're going to enter in the corresponding p-value, which for SWE J1 is going to be 0.018. So you've done a few things to look at the normalcy of your data set. So based on that, you're basically going to rank your data variables and sites going from the most normally distributed, again, looking at those QQ plots, the histograms, and the p-values for the Shapiro-Wilk test. You're going to be basically putting in the most normally distributed data set in position 1 and the least normally distributed data set in position 4. So the last question here is you're going to be using the mean and standard deviation values. You're going to be using those to determine these Z values, okay? So remember what the Z values are. The Z values are basically, right? You calculate your Z values basically taking the X minus the mean divided by the standard deviation. So imagine that we have an observed SWE at both site J1 and J4. We're going to take that 14, that's going to be our X, our observed value, minus from that the mean, we determined the mean before, divided by the standard deviation, which we determined in the descriptive stats, and that's going to be our Z value. And you're going to enter the Z value for each of these sites and variables up to 3 decimal places. Okay. So that's about it for the lab. Again, there's videos embedded in there to help you out as well. Pretty straightforward lab, really. So have a look at it, and it also will help you a little bit for this week's midterm. Okay, so again, we will not be having lecture this week because you guys have your exam. So I'll let you guys hop to it and study for your exam and have a look at the lab. Otherwise, I will, good luck on the exam, and I will be standing by on Thursday for email. Okay.